Okay, hello and welcome back everybody. We're moving on to section 4.4. It's called separation of variables. It's actually maybe one of the more common topics in traditional PDEs course, maybe the most common topic. More common than Fourier methods, more common than method of characteristics, etc. It's a really common method in a lot of books, and I actually hate it. There's something about it that just feels wrong to me. I have no idea if any of you will agree, but that's my perspective. You'll see that it's relegated to a single section, but I'm going to teach it anyway because you're going to pass this course, go into the industry, and somebody's going to ask you to solve a PDE with separation of variables. If they see that you've passed PDEs on your transcript, you should know what they're talking about. So we're going to go through it anyway. We'll see if you agree with me on how much you do or don't like it as a solutions method, but we're going to go through it and see why maybe a lot of other people like it. So we start out just with a little bit of motivation. So we're going to jump back to the Fourier multipliers, and we're going to jump back specific to constant coefficient second order PDEs. So you'll notice that A, B, and C, A being a matrix, B being a vector, and C being a scalar, I've gotten rid of their dependence on the spatial variable x, so now they're just constants. And if we represent this as a Fourier multiplier, you just take the Fourier transform of everything that's not phi on the left-hand side. What you'll get is minus y dot ay plus I b dot y plus c. It's going to be some quadratic polynomial in your conjugate Fourier variables. And so it has a Fourier multiplier representation, which means that you can actually solve this problem just by inverting the Fourier multiplier with an inverse. And since it's a multiplier, it's truly a function, and the inverse is truly the reciprocal, which means that your solution, phi, to that differential equation will actually look like this. So D is the Fourier transform, whatever was on the right-hand side of the PDE, so the inhomogeneous term, forcing term. But you're going to divide by n because that's what it'll be to invert that Fourier multiplier. However, at this stage, if I represent my solution in its Fourier transform representation, and I expand my dot product in the complex exponential, and then also expand my volume form, and then separate every single one of these integrals to each of the directions. So I've separated all of my d directions of integrals into independent integrals. If I have the ability to take this function, this ratio of two functions really, suppose I have the ability to represent it just as a product of all of the variables. If I have the ability to represent it as a product of all the variables, then my integrals reduce, instead of nested integrals, I actually end up with just a product of integrals against a product of Fourier transforms. And this isn't actually out of this world. The reason why we shouldn't expect it to be out of this world is something like, recall e to the t delta in Fourier multiplier world was e to the t. Let's say we're in two dimensions, z1 or z squared plus w squared f, and that's actually going to be f inverse e to the tz squared e to the t w squared. So there's one example of maybe a non-trivial Fourier multiplier that does split. It's a function of two variables, but it splits as a product of each of those variables independently. So it's somewhat common that this happens, that whatever Fourier multiplier is solving your PDE for you splits into a function of multiple variables. And then that means that the integrals no longer nest, and the integrals themselves of each variable independently become a product of each of those variables independently. And once we see them as a product of all those variables, what are each one of these integrals? Those are one-dimensional Fourier transforms in the inverse direction. And so you find out that your original solution was actually just a product of solutions of each of the independent variables. Okay, so it's a product of one-dimensional solutions. Now that really is relying on this structure of the Fourier multiplier. And so whether or not that's a possibility is kind of up in the air. But as I already showed, like with the heat equation solution, it's true. And people have noticed that for a lot of situations, it's actually true. So it's like a nice assumption to make, even though maybe it's not always true. And I use the word assumption. That's basically the same as this word ansatz, if you've never heard it before. An ansatz is an assumption of the structure that your solution takes. So you make an ansatz when you assume the solution takes a particular form, and then you show that actually was a correct assumption to make. So I've introduced the definition here as separation of variables ansatz, which is to say this doesn't necessarily only apply to second order PDEs. It applies to any sort of PDE. So they're just giving you an arbitrary order, nth order PDE. And we call the separation of variables ansatz the assumption that the solution is a product of d copies, if I'm in RD, d copies of one-dimensional functions of each of the d independent variables. So that's the ansatz. That's kind of the whole point of separation of variables, is making that assumption. And that assumption provides us with a method of actually trying to solve maybe the PDE that we're actually looking for. So what is that method? I'm calling it a definition because I can't really call it a theorem because it doesn't always work. And in fact, I tried really hard I delved deep into the literature to figure out if there was a theorem hiding behind this instead of just a method. Just to try to say, hey, if the PDE satisfies some bullet point collection of conditions that we can apply the separation of variables method. And it turns out nobody really has a good interpretation of what this bullet point of conditions on the PDE should be. So it's kind of a black box where we don't know why it works in the situations it works. I mean, you kind of know why because you try it out and it works. So clearly that's why it works. But there's nothing in the theory hiding behind all of this telling us that it should work from the beginning. So that's really my internal struggle with this, that I don't like the method because we can't ever tell if it's going to work before we try to make it work. But it turns out to work fairly often. So we're gonna go through the definition as a definition and not a theorem. So the method, if we start with a second order PDE, the method is to start with the ansatz. Not a big surprise there. So we're just going to assume that our solution takes the form of d functions, each of the d variables, and then we're going to plug them in. We're going to plug this collection of d products of functions in for every phi in the PDE. And you end up with a nice, lovely, giant collection of functions in your PDE. What you try to do, right, the kind of the important part of step 2. So step 1 is just making the assumption. Step 2 is isolating all of the phi1s to the left-hand side. Okay, so if you can isolate all of the phi1s, and in fact x1s, right, so we need this term x1. So isolate all phi1 and x1 to left-hand side, everything else to right-hand side. So that's really what you need to do. Isolate everything with an x1 or a phi1 to the left-hand side. Since this is second order PDE, we're only going to have terms of phi1 up to second order. And I can use the notation prime here. This is kind of cool, right? Once we make this assumption, we can use the notation prime because actually phi1 is a function of only one variable. So the prime is well defined as technically the partial derivative in the x1 direction, but it's also the ordinary derivative in the x1 direction because phi1 only depends on x1. So I've got a function of x1, phi1 prime, and phi1 double prime in comparison to all sorts of other terms. These are all your x2s, x3s, phi7s, etc. Every other term you could possibly have is on the right-hand side. But what this gets you, so moving to step 3, what this gets you is that the entire left-hand side depends independent, that's a nice little oxymoron, depends independent of x2, x3, ... Well, what that means is I could move x2 or x3 around, and then f1 should move around, right? But it can't because it doesn't have any dependence on x2 or x3. So if it doesn't have any dependence on something, and it's equal to something which clearly does have dependence on it, both sides, so I'll say at this point, at this stage, both sides must be equal to a constant. And in fact, you should just pause right here and internalize this. At this stage, both sides must be equal to a constant. This is really what separation of variables is all about. Once we perform this separation where we can isolate all terms to the left-hand side and everything else to the right-hand side, you gain for free that both of them are equal to a constant. So this is kind of the big jump, and the constant's what's going to allow us to solve these PDEs. So that's what's going on in step 3. We say, okay, since it's equal to a constant, we can just, instead of writing it as equal to g, we can say it's equal to lambda 1, our first constant, more or less. And now that it's a function of a collection of one-dimensional functions of one input and the derivatives, that is just an ODE. By definition, that's a one-dimensional ODE in the independent variable x1. And these are fairly easy to solve, right? We have a lot of ODEs methods that can solve those for us. And then what we're left with, the rest of the terms, g1, is going to be also equal to lambda 1, the same constant. That's going to be a collection of all the other terms. But if we just focus, let's just focus for now on our ODE that we actually want to solve, because that's going to tell us what phi1 looks like. Right? We solve the ODE right there. We're going to figure out what E1 looks like. So step 4, solving the ODE for phi1 of x1 gives the first term in the PDE solution, dependent on lambda 1. Right? If I jump back up to my ansatz, I just found an ODE depending on lambda 1, which, or I should say whose solution, is phi1 of x1. So you just have to solve an ODE dependent on lambda 1, and the solution will be phi1. In step 5 then, we go over to this G1 where I said, both terms that had been equal to each other up top here, both of these terms had to both be equal to the same constant. They were both constants and they were both equal to the same constant. Now if I look at the other term, the first term gave me an ODE, the second term gives me something else. But what can I do with the second term is I can repeat the process. Repeat process. But now phi1 of x1 is gone. Right? And so the fact that phi1 of x1 is gone, I've reduced my system by exactly one entry. And you repeat the process, you move all terms with phi2 or x2 in them to the left-hand side, and everything else to the right-hand side. Okay, so that's just like before. I move everything with dependence on x2 or phi2 to the left, and then everything else to the right-hand side. Now the right-hand side will depend on lambda 1, right? Because if I'm pushing a lot of terms over to the right-hand side, everything but x2 and phi2, if I push all the rest of them to the right-hand side, it will be a function of lambda 1. But everything else in there won't depend on x1 because I already got rid of x1 up here. So it's not going to depend on x1, it's not going to depend on x2 because I moved everything with x2 to the left-hand side. And then we repeat. So since the left-hand side is equal to a function of x2 and everything else is not a function of x2, they must both be equal to a constant, a new constant, lambda 2. And if they're both equal to a new constant, then actually I can set them both equal to that new constant. And now I have an ODE for phi2 in terms of x2 dependent on lambda 2, and then g2, everything else is dependent on that constant as well. But now I solve this new ODE dependent on lambda 2, and when I solve that ODE, then I found phi1 the first time I did the process, and phi2 the second time I did the process. And so my final step, step 6, not technically the final step, but the final step in finding the general solution, is to just repeat this process. I think you can kind of understand. I was just repeating it over and over again. We're going to repeat this, and every time we repeat it, we eliminate dependence on one of these variables. And so after d steps, you're going to eliminate dependence on all the variables. You'll find out that there is only d copies of lambda, because once you get to the very last step, then at the very last step, then this is a function of x d minus 1, and this will be a function of x d, and they're both going to be equal to the same lambda. So at the d minus 1 step, they'll both be equal to the same lambda. So you only have to do it d minus 1 times, but you're technically solving d total ODEs. And then you're going to get each of your solutions, phi1, phi2, through phi d, dependent on the rest of them. Now, each of your solutions, except for the very last one, will depend on only one constant. So each but phi d will depend on only one constant, just by the nature of how we were solving for g every time. G, we pushed all the constants into the function g, and so the ODEs themselves only depended on the other constant, except the very last case, in which case g will be a function of all of the lambdas. And so the very last solution will care about all the constants. We'll incorporate all lambda 1 to lambda d constants, d minus 1. So we'll have one fewer number of constants than our total number of dimension that we can work over. So that's going to be our final solution. We're just going to multiply all of those together. That'll be a general solution in the sense that general means up to constants, right? Back in the ODEs, you would find a general solution. You had like C1 and C2 sitting around. Or if you increase the dimension and the orders, who knows how many constants you have sitting around, but that's really what these constants are. It's our collection of parameters that we can use to fit initial or boundary conditions. So the lambdas will help us fit initial or boundary conditions. Just like with ODEs, when you would find a general solution first and then find a particular solution by satisfying the initial and boundary conditions. So the way this works, the way we're going to find the lambdas to satisfy initial or boundary conditions, if I jump back up to my original PDE, it was linear. So I'm only applying this to linear PDEs. Things get a lot harder if I choose nonlinear. Actually, it really just doesn't make sense if I choose nonlinear. So I'm only going to do this for linear PDEs. And what do we know about linear PDEs? Is they satisfy the principle of superposition, right? So the principle of superposition says that I can add infinitely many solutions with arbitrary choices of these constants to gain the overall solution. So I can add arbitrary choice of these constants to gain a particular solution. And so you have to find whatever that addition of specific choices of constants is going to give you particular solutions that satisfy initial or boundary conditions. This could be a sum, as is notated here, or an integral. Because in fact, an integral is just it's a sum of infinitely many terms over infinitely small intervals. So it could actually be an integral instead. So I've notated it as a sum there, but you should keep in mind that can also be an integral. So what you have to do in the very last step, if you decide that you need to satisfy initial or boundary conditions, is actually find the specific collection of lambdas that's going to satisfy them for you. So this seems really arbitrary for now. You maybe don't really understand what it's trying to say. We're just going to go through examples. This is really an example-driven process to learn it, but I've technically provided it for you. There's a remark there. You can look into it if you want to. I don't think it's terribly important. But let's look at this example. This is how we're going to solve Laplace's equation. We're going to solve some of the Holy Trinity, actually, but we'll solve Laplace's equation using separation of variables, okay? So here we are. We've got Laplace's equation. Delta phi equals 0. We're going to give ourselves a half plane, okay? So this is the real numbers in the x direction and the positive real numbers in the y direction. So that's really the positive half plane, is omega. So we're going to solve the ODE in there. I'll mark that as omega is up here, and so the boundary is kind of this x-axis. There's x in r and y is equal to 0. That's the x-axis. And then on the x-axis, we say we're equal to cosine of x times a Gaussian. Okay. So we know that we look like cosine of x times a Gaussian here, which I guess probably looks something like that. And we're going to try to extend whatever this would maybe look like into the upper half plane here. I don't know how it extends, but we're going to try to find that using separation of variables. So we're going to follow our procedures to find that. And to do this, I'm literally just going straight back up here, and I'm going to go through steps 1 through 8. So I would advise that you do that too if you're looking for it. Okay, so we're going to make the separation of variables ansatz. Instead of using subscripts here, since my variables are x and y, and I have access to phi and psi, I'll just say, okay, this is, our solution's a product of the function phi of x and psi of y. Then what I do is I grab this product and I plug it in to the PDE. If I plug it into the PDE, we're calling 2 dimensions. The Laplacian is partial x squared plus partial y squared. So those are going to hit those two functions. And if I solve those out, we get the bottom line here. Phi double prime of x, psi of y, plus phi of x, psi double prime of y. And because it says the Laplacian is equal to 0, that whole thing's equal to 0. So in reality, what I'm looking at is this PDE. Even though it looks like an ODE, it's truly a PDE because we do have derivatives in both the x and y direction there. So that's what we have after making the separation of variables ansatz. That's what the PDE itself becomes. That PDE becomes the collection of derivatives below. And we need to isolate all terms with one of the variables, right? So let's isolate all terms with the variable x in them, which means I'm looking at this phi and this phi, and I'm going to bring them to the left-hand side. You go through your basic algebra to do that, and you recover that phi double prime of x divided by phi of x is negative psi double prime of y divided by psi of y. And then the nice thing about separation of variables, the most important part about separation of variables, is once you've done this, once you've isolated everything with one variable to the left-hand side, both sides must be a constant. This is the definition of separation of variables. Both sides must be a constant, the same constant, right? So we're going to set both sides equal. That's the left-hand side, equal to a constant. Here's the right-hand side, equal to a constant. Now, I chose a constant lambda squared. You may be wondering why I chose lambda squared instead of lambda. Why didn't I give it a subscript 1? I didn't give it a subscript 1 because we're in 2 total dimensions. The total number of lambdas you need is dimension minus 1, so you need a total of 1 lambda, 1 total constant in this case. And the reason I chose lambda squared is just because it's a second order ODE. It's going to look prettier if we choose lambda squared. So it's to our advantage. It'll look prettier if we choose lambda squared. Let's just go with it for now. You'll see why. So what I'm going to do in my next step, in step 4, is I just take this as an ODE and I solve it as an ODE. If I rearrange it, right, it's probably smart to rearrange it to make it look like an ODE that we're a little more used to in reality, but it's a very easy ODE to solve, right? It's separable if you want to do it. It's linear if you want to do it. It's absolutely whatever you want to do to solve this ODE. You're going to find out that it's a C1, which depends on lambda, C2, which could depend on lambda, So I've got a collection of constants, undetermined coefficients, C1 and C2. And then there are these complex regular exponentials, e to the lambda x and e to the minus lambda x, which solve this ODE. So that's just going through your basic ODE solving formulas. And we do the same thing for step 5, which is thankfully our G, or really our terms that don't depend on X, are already in ODE form. That's a consequence of us being in 2 dimensions originally, is that we only have to go through this procedure once. So we're going to end up solving this ODE as well. Rearranged, it looks like that. The only difference is that my lambda was positive lambda squared there. It's a negative lambda squared here. The consequence of the negative, what's the square root of -1? I and negative I. So we're going to pick up some imaginary exponentials for psi is the only consequence of having a plus or a minus. Okay, so what does that mean? We found phi of x via an ODE. We found psi of x via an ODE. And we know from the beginning, with our separation of variables ansatz, our solution of x and y was phi of x times psi of y. So we're just going to grab these two functions and multiply them together. When we grab them and multiply them together, that's what we have here. They all depend on lambda, right? They're still in general form and they depend on lambda. But that is truly the general solution, as it depends on whatever lambda we've chosen. Now what we know is that under the principle of superposition, we can add infinitely many of these together if we want to. Now what would that look like? This is what I was saying. The sum over here may actually be an integral. It's totally up to you what you want to use, if you'd rather use a sum or you'd rather use an integral. This is where you kind of have to be a little bit clever and talk to yourself and say, oh, that is a square integrable function defined on the real line. I'm probably going to want to use the Fourier transform, not the Fourier series. If it were a bounded interval, then we use the Fourier series, and we'd have a sum there. If it's an infinite interval, we're probably going to use the Fourier transform. And so I'm going to integrate over all of my lambdas. So my true general solution is whatever this integral is equal to over any choice of C1, C2, D1, and D2. That's really the true general solution to that Laplacian, the Laplace equation, this one, defined over this area. Now what I need to do is satisfy a boundary condition. So I have to figure out what C1, C2, D1, and D2 need to be to satisfy my boundary condition. What can I do to do this? The boundary condition occurs at y equals 0. So there, that y is going to be a 0. That y is going to be a 0. Those exponentials reduce to the number 1, and we just get d1 plus d2, dependent on lambda, which basically means that let's just let both be 1. Both add to 1. So we can forget about it. Alternatively, you think about absorbing them into C1 and C2. We should really only need two parameters to make this satisfied, to satisfy that particular cosine. So we're going to set up this equation, which is the boundary value equation, right? That's the value that it needs to achieve on the boundary. And we set it up, and now we ask ourselves, what should C1 be? What should C2 be? Well, if we let lambda be IR, okay, IR, and we make a little change of variables. Once again, we can really forget about these. I know I've kept them around, but that's where I get rid of them. And we figure it out. We make our change of variables. You get that there's this C1 star of lambda, that's e to the I lambda x, and then C2 star times e to the minus I lambda x. And we need these integrals all together to give me cosine x e to the minus x squared over 2. So that's saying that these, which are just Fourier transforms, need to give me cosine x e to the minus x squared over 2. Well, how do I figure out what C1 and C2 should be? Well, it's just an inverse Fourier transform of this function. So all I need to do is find the inverse Fourier transform of that function with the conjugate variable lambda, right? I'm integrating over lambda here. So that's my conjugate variable. I'm going to compute the Fourier transform of that. And you find out that the Fourier transform of that function is e to the minus lambda plus 1 squared over 2, e to the minus lambda minus 1 squared over 2. And so you set that up for C1, similarly with C2, right? And we end up with setting that for C1 and C2. And that means in my general solution, that's the one all the way up here, this general solution, I'm going to choose the specific value of C1 that I just found, the specific value of C2 I just found. D1 and D2 just need to add to 1. And you can set them both equal to 1/2 if you want. And so I plug those in for C1 and C2. That's C1. Recall D1 was just 1/2, and D2 was just 1/2. There's C2. And then if D1 and D2 are 1/2, you pick up a cosh. You could just do that algebraically if you want. At this point, you ask your computer, hey, can you actually calculate this for me? So use a computer algebra system. To calculate this. And when the computer algebra system calculates it, you get the following as your solution. So you get this Gaussian of y squared minus x squared, and then you get cos x, cos xy, and cos y, and then you get sin x, sin xy, and sin y. And that's just going to be your solution to this particular Laplace's equation. We can plot it here. Notice this is that boundary condition I was talking about from the beginning. That's satisfied, and then we're kind of extending our membrane out to the right. And because we don't have any like infinite condition on the membrane that it needs to decay or anything, you can see the membrane gets quite excited towards infinity, so it grows really fast. But anyway, yeah, it's a tricky process. So we're going to stop there for today and finish up with 2 more examples in the next video, because this is the sort of thing we should take a little bit of time on. Like I said before, I don't really love it because you'll notice all we reduced to was the Fourier series. And so Fourier methods are actually a stronger version than separation of variables methods. Now, what we do get around is the fact that this really wasn't technically a Fourier method because we were working on R. We're working on this space, right? R cross R plus, which that sort of a space doesn't lend itself to regular, I'll put that in quotes, regular Fourier methods. But it's really not hard to translate into a regular Fourier method space from this space, or technically it's a Fourier transform cross a Laplace transform is what you would use to solve over this sort of a space. So I kind of like the regular methods better than the separation of variables. We kind of had to make an assumption and not knowing that it was the right assumption to make. But then it does end up working and we get our solution. Hey, everybody's excited, but my perspective is still that it's not quite as powerful as other methods. Anyway, it is definitely a difficult method, so we are going to spend a lot of time on this, including the next video where we go through some more examples. I'll see you then. Bye.